A lot of Chapter 16 is not covered in the AP exam, so we're just going to spend time working on the parts that are covered on the AP exam. And the first part has to do with dissolving salts. So we have a solid, and we're going to break it into ions, and this is called solubility, the ability to dissolve. So notice in these pictures, we have a salt that it's originally put into the water, and as water surrounds it, it's going to break off the pieces and form ions. But at the same time, some of the ions will stick back onto the solid. So we get an equilibrium situation where you have the solid breaking apart into ions at the same time that the ions are sticking back onto the solid. And so what we can figure out by doing equilibrium calculations is whether most of the salt will dissolve or whether most of it stays together as the solid. So we're going to use K again, just like last time, for equilibrium. This time it's called KSP. So KSP has to do with the solubility product that's going to form. Now notice that for the KSP equation, it's not a fraction. And that is because when you're doing solubility, you're starting with a solid. If we look back up here at this example, we're starting with a solid, and solids are not included in K equations, and so we have no reactants for the K fraction. And so all we have are the two products, which are the two ions. But you still square them just like you would before. And you can go back and forth. So if you know the solubility of an ionic solid, you can use that to calculate the KSP. Or if you know the KSP, you can use that to calculate the solubility. We can also use KSP to compare several different salts. But we can only do that if they have the same number of ions that they break into. So they have to break into the same number of ions or else we can't compare them. But if they do, then we can use this general rule, just like before, that the higher the KSP, the more ions you have, which means the more soluble it is. So here's just an example. Notice that in the ice table, we cross off the solid. So be careful if you're doing solubility. Anytime you have KSP, you're not going to have that reactant. You just go towards the zeros for the products, but be really careful. This little note over to the side says that if there's a coefficient in the balanced reaction, you're going to end up seeing that twice in the K equation. So make sure you see it twice. It's in front of the X because that's a ratio, and then it's also squared because that's the rule for the K fraction. So just make sure you have that in there twice. And this will help you a lot. When they say what is the solubility, if they're asking you for solubility, first of all, it's going to be in units of moles per liter, and it is the amount changed. So it is when you solve for X, that is the solubility. It's not, you don't use the coefficients anymore, it's just plain old X. X is the solubility. And again, it's in units of moles per liter. And if they tell you the solubility, then they're telling you the value for X. There's another little problem with this is that you have to use the concentration of hydroxide or H+ from water if you have it for KSP problems. So notice that if we have magnesium hydroxide, so first of all, we're not going to include this because it's a solid. We break it into Mg2+, and we have 2 hydroxides. Don't forget to balance the reaction. We're starting with 0 magnesium, but notice that the hydroxide is the amount of hydroxide in water. And you only have to do this for the KSP problems. And then you've got your X's, 2X because there's a coefficient. And then also, there's a mistake in here. Don't forget to square it. So that should be squared as well. The common ion effect we've talked about before, but this is the idea that if you add an ion that's already in the reaction, that it's going to shift the reaction based on Le Chatelier's principle, and it will lower the solubility. So if you have like AB is the solid, and it's forming A+ and B-, and if you throw a whole bunch of B- into there, so you increase this, it's going to shift it back towards the solid, and so we say that solubility will decrease. So the solubility is lower because it's shifting towards the solid. So that means fewer particles of the solid are breaking apart. Also, we can talk about it in terms of pH. So this says if an anion X- is an effective base and HX could be an acid, then the salt MX will show increased solubility in an acidic solution. Here's what that means. So if we have MX is our salt, this is the solid, and it's breaking apart to form these two. And what they're saying is that X- is attracted to hydrogen. And so what happens is that if you add an acid to the solution, so let's add some acid, these two will stick together to make HX, make that weak acid. And so what you're really doing is you're decreasing the amount of X- in the solution. And so taking out some X minus, because it's no longer X minus, now it's HX, is going to shift the reaction to the right. Remember, if you decrease the products, it will shift it to the right, which will increase the solubility. And that's what that's saying right there. And these are some examples of really good bases. A good base will react with H plus when the acid is added, and therefore it will take away that ion, and so it'll shift it towards the ion, which increases the solubility. All right, let's skip over to the next section. 16.2 has to do with qualitative analysis, and we're going to do a digital lab of this later on this year, but this is basically where you can figure out what something is. Qualitative means identifying something or telling what it's like, and so you can identify something based on what you mix it with. So this is just an example of a flow chart. If you have a solution of these ions and you add cold hydrochloric acid, you're going to get precipitates. Then you can heat it, and if you get a solution of lead, it's going to end up being yellow. If you don't get yellow, you'll get one of the other two. So then you do another test on it, and you see if it forms something. So if this one ends up being black, you know it's this one. If it ends up being white, so it's just kind of a way to identify what things are. But you would have to be given this chart. You don't have to. You're not expected to know that. And our last section is on complex ions. And in AP Chemistry, they really just briefly introduce what they are. And the only times I've seen questions on these on the AP exam is multiple choice questions where they list lots of compounds, and then they ask you questions like which one is hybridization, which one has a triple bond, and all kinds of questions about it, which one is polar, and they might say which one is a complex ion. So you just need to be able to recognize when you see it. So first of all, this is a polyatomic ion that consists of a central metal atom or ion bonded to other groups, and those groups are called ligands. So just some new vocabulary for you here. So there's some examples down here. Notice that you have a central metal ion atom, and it has the ligands right here, and then it's going to have an overall charge as well. So it's kind of like you have a metal salt with an overall charge. That's how you can recognize it. And then that can be bonded to something else. So since this was a -1 charge, it can bond to the sodium and form what we call coordination compounds. So lots of new vocab. Complex ions are just a metal bonded to some polyatomic ions. And those polyatomic ions are called the ligands. And then if that complex ion bonds to something else, it's called a coordination compound. This is a good rule. The number of ligands is usually twice the charge on the metal. So for example, that first one, AgCl2, Ag is +1, so that's why there's 2 chlorines, is that it's usually twice the charge on it. Same thing for the next one, copper is +2, so then we have 4 ammonias bonded to it. And overall, all the charges will add up together. So ammonia doesn't have any charge, NH3 is neutral, and the overall charge is +2, which means that copper is also +2. But notice over here, zinc is +2, you had to memorize that one. Hydroxide is -1, and we have 4 of them, so that's -4, and that's where they're getting that -2, is because +2 and -4 gives you -2. And you can also do a K expression for this. It's called Kf for the formation of it. And we'll do some more problems with this as in the progress check for some examples. And that is it for chapter 16.